Hi, are you interested in the universe? Are you interested in finding out some of the unanswered questions? Do you want to know what dark matter is? Do you want to know what dark energy is? Do you want to know how the speed of light can always be constant? Did you know that we can work out the gravitational force of any point in any galaxy using this formula here? Did you know that we can take the orbital velocity of any point in any galaxy and calculate the visible mass? Or that we can take the visible mass of any point in any galaxy and calculate the orbital velocity? So if you want to know more, then you have come to the right place. Ladies and gentlemen, boys and girls, hello, welcome. My name is Mark Hatfull, and today we are going to talk about the universe. We're going to try and come up with a single model of the universe. How are we going to do this? Well, we're going to start with the basic elements. We're going to look at what we already know, and then we're going to look at what we don't know and what questions we have left to answer. And then we're going to see if we can put that all together and come up with a single theory that incorporates all the elements of the universe and is consistent with observable phenomena, and also explains the unanswered questions that we in the universe that we haven't yet discovered. We're going to talk today about what dark matter is. We're going to talk about dark energy and what that could be. We're going to talk about why the speed of light is constant. We're going to talk about what gravity is, why mass bends space-time, and we're going to try and put this all together in a single theory, which is simple, logical, methodical, and easy to understand. So it's a big ask. There's a lot to cover, and so hopefully we can do it reasonably quickly, and we will all be better off afterwards. All right, so how am I going to do this? So first of all, I'm going to look at a model that already exists. We're going to look at what makes a model a good model, and we're going to see if we can incorporate that into our model. So we're going to look at what we already know, what are the elements of the universe, how do they all fit together already, how are they not fitting together, what's missing, and can we do any better? All right, so what does a good model look like? So this is the model I've chosen. Many of you might recognize this. This is the tree of life model, which is often used in biology. This is a fantastic model because it takes an incredibly complex and enormous topic and it simplifies it into something that's easy to understand, logical, and it can be put into a single piece of paper. And so here we can see that the tree of life um, uh, teaches us about all life on Earth, everything that's extinct and alive today. It's millions and millions of species, and it breaks it down into simple fundamental principles. So if we quickly summarize, we can say that all life on Earth is based on cells. If we start with single cellular organisms, then we can go into different subtypes, and we can start with fungi or animals or plants, and then as they become multicellular organisms, they can evolve into more complicated animals and life forms, and then we can go further down the tree into fish and amphibians and mammals and birds, and we can even go into individual species. So here we've got potentially millions and millions of types of life, and we can categorize them all through the same fundamental principles and illustrate that in a simple, easy to understand model. So what does a good model look like? Well, a good theory should be built on sound principles. Everything should be interconnected through these principles. There should be very few or no exceptions at all. And if there is an exception, it should be easily understandable. And then once we understand the topic, it should be quite straightforward. So we're using the tree of life as an example. We can see that everything's built on sound principles, that all life on Earth is made up of cells. Everything is connected, so we can see all life is connected through this tree, and then there are few or no exceptions. If we were looking for an exception, we may say something like a virus is not an intracellular organism, and a virus is not on this chart. And so if we consider that a virus is a life form, then that would be an exception to this model, and then we'd need an explanation for why there's an exception. And in this case, it would be that a virus doesn't have its own cell, but it lives inside other cells. So it needs to live inside a cell to survive. And so there we've got a clear, easy to understand exception, and then finally we've got a topic which is easy to understand and makes sense. So that is our goal for today. We want a model of the universe which fits all these principles as well. And at the moment, that's something we're lacking, which we don't have in current physics. So what do we know? What questions do we have? Well, let's break this right down to absolute basics. Let's start from the beginning. So if we look out into the universe, what do we see? So this is a picture of space, and as you can see, when we look out into space, we can see a number of things quite clearly. So these would be good basic building blocks to start with. So first of all, we can see the universe. No matter what direction we look in, we can see that the universe is similar in every direction. So there must be some underlying basic rules of physics which apply universally throughout the universe. And so we can see that if we look in one direction, we can see that the universe is made up of mass and space and gravity, and we can look in another direction, we can see that the universe is also following those same rules of physics in every part of the universe. We can see that the mass is evenly distributed throughout our universe. We can see that space is vastly distributed throughout our universe, and that's the same everywhere we look. And so the rules for one part of the universe have to be the same for other parts. And all these things that we're seeing are all part of this universe, so they must all be interconnected. And so we can break down what we see when we look into the universe as mass. We can see it distributed through space. We can see that mass moving through gravity. We can see that gravity and the mass aren't enough on their own to compensate for what we appear to be a lot more mass in the universe. So we have this thing which we presume is dark matter. And the reasons we presume that there's a thing called dark matter is things like gravitation or galaxy rotation curves, lensing, cosmic background radiation, and galaxy collisions and other things like that. So we need an explanation for these phenomena that we're observing, which isn't explained by the current mass, space, and gravity that we currently have. So we need to find a reason for this dark matter. If we also look out into the universe, we can see that there's electromagnetic waves and light throughout our universe. And if we look at our universe over time, we can see that it's moving and changing. And so that also shows us that the universe is expanding, and it's expanding at an accelerated rate. So we need an explanation or a reason for that. And at the moment, we've come up with a kind of placeholder term, which is dark energy. But we're yet to find out what dark energy is or how it works. So this would be a good kind of starting spot to go from, to look at these elements individually, find out what we know about these elements, find out what we don't know, and see how they all fit together. All right, so let's start with the universe. What do we know? We know it's big. We don't know how big it is. We don't know if it's infinite or if it's finite. If it's finite, we don't know what's outside our universe, where our universe ends. And so this is probably one of the first questions we need to look at and see if we can find an answer to. What else do we know? We know it's expanding, but we don't know why it's expanding. We initially thought it was something to do with the Big Bang, but now we know that it's expanding at an accelerated rate. And if it's still accelerating, that means there's an ongoing force still contributing to the expansion of the universe. We've named this force dark energy, but we don't know what dark energy is. We don't know why our universe is expanding. We don't know why the expansion is accelerating. All right, what else do we know? We know that the mass of the universe is evenly distributed throughout our universe. This is another question we need to answer. Why is it evenly distributed? If we just said that our universe is expanding, then how does the distribution of the universe remain evenly spaced? How is it still homogeneous, especially if it's moving? So just a quick example of that. If we imagine that our universe was once smaller, as it's expanding and it's accelerating, then we would expect that as it expanded, that the mass on the outside of the universe would be moving away faster than the mass inside our universe. So if we looked at any individual plane of our universe in any direction, we would expect that there was areas in the universe that were sparser, less dense, moving away faster. And we'd also, on the other side, expect to have areas which were denser, slower moving, and closer packed together. So we don't see that when we look out in the universe. We see everything looking exactly the same in every direction. And so this doesn't fit with what we would expect to see. So we need an explanation for that. Now, some people might be saying, well, maybe all the mass of the universe is expanding equally outwards at the same time. And so if that was the case, then we might see something like this, where we get a ring of a universe. And if that ring was big enough, then theoretically, to us, it might appear flat. So if that was the case, then a neighboring mass would be moving away at a similar speed, and it would be similar spaced and evenly distributed. But again, if we looked in other directions or other planes, we would find that there was a big hole in the middle where there's nothing inside the universe and there's nothing outside. It would all be on a flat, equal plane. And again, that's not what we see. And so we don't have an adequate explanation for why we're seeing a completely homogeneous, evenly distributed mass throughout our universe in every direction, especially the fact that it's expanding. So there's the facts about our universe, and there are a number of unanswered questions which we have yet to explore. What else have we got? We've got dark matter. So I'm not going to go into all our current theories, and I'm not going to go into all the basics. If you don't know what dark matter is, or you don't know the phenomena, go and research it, Google it yourself, and or if you're not following any of this, just pause the video and get up to speed, because I want to keep this short and simple, and I don't want to go into everything today. Anyway, dark matter. What do we know about it? We think there's some matter out there which accounts for up to 85% of the mass of the universe. Why do we think this? Well, the primary reason is something called the galaxy rotation curves. And this is a picture of a galaxy rotation curve here. So basically what this shows is that according to our theories of gravity, as we get further out from the center of a galaxy, we expect that the force of gravity would decrease. And as objects rotate or orbit a galaxy due to the force of gravity, as the gravity decreases, we'd expect the velocity to decrease as well. And that's what you see on this blue line, is what we would expect to see from the mass that we see in a galaxy. However, what we actually see is the red line, and that is where the further out from the galaxy you go, the faster the rotation curve, or at least the rotation curve doesn't decrease in velocity. And so in order for that to apply to current physics and the current understanding of gravity, we would need considerably more mass. So hence we've come up with this term that there could be some dark matter. There's other phenomena that also aren't explained, which could be attributed to dark matter as well, stuff like gravitational lensing, cosmic background radiation, and also galaxy collisions. And I'll talk a little bit more about them later on as well. But for now, the primary evidence for dark matter is these galaxy rotation curves. And so we're going to cover that in more detail later too. All right, then we've got gravity. So we started with Newton's law of gravity. That explains the motion of objects on Earth and in our solar system pretty well, but it doesn't actually tell us what gravity is. It just tells us how it behaves. So then Einstein came along and he came up with a theory of relativity. And basically he described space and time as a four-dimensional structure. And so he says that mass curves space-time, and this results in the force of gravity. But again, there's a few things that aren't quite complete in this theory. So it's a good theory, it's widely accepted, but it doesn't explain why mass curves space-time. We don't have an explanation for why it's doing that or how it's doing that. And it doesn't explain a few other things. So at extremes of the scale, it breaks down around black holes. We don't have an explanation for galaxy rotation curves, and it doesn't work on the quantum level, which is important because we want to know how gravity works around particles. And if we can do that, we can fit it into the standard model. So although we have a reasonably good theory for gravity, there's still a little bit of patching up we need to do. And so today we're going to find actually a completely new theory of gravity, which answers these questions. Okay, so we'll try and skip through these pretty quickly. We've also got electromagnetic waves and particles, so quantum mechanics. We're going to basically bunch that into light today, so we're going to be talking about light. So we know that light has all the properties of a wave, but we don't know why light travels through a vacuum, and we don't know why the speed of light is constant. So we know the speed of light is constant, we observe it and we measure it, and we always find that it is constant, but we have no explanation for why it is constant or how that is possible. And it's almost counterintuitive to think of a mechanism of how it's possible for light to travel at a constant speed. So again, we'll try and answer that for you as best we can today. Okay, and that just leaves us with time. So, as I said, Einstein's theory of relativity is a basic understanding of gravity at the moment. That also incorporates space and time. And so, according to general relativity, space is relative, time is relative. Time change is due to movement. Time change is due to gravity. Yet we have no idea why or how time changes due to movement or gravity. And so, again, let's look into that and see if we can put that into our model. All right, so we've taken some elements of the universe, we've looked at the basics, we have found out what we observe, and we have found questions that we have yet to answer. And so we can put that all into a table, which looks like this. And I'm going to go through this quickly again, because the universe is a big topic to cover, and I want to get into it. So when we see the universe, we see it's big, we see it's expanding, we see the expansion is accelerating, we see there's things called we see things that could account for dark matter, we see things that could account for dark energy, and we can see that the mass of the universe is distributed evenly throughout, despite it constantly changing, growing, and accelerating. So our questions for the universe is it infinite? Is it finite? If it's finite, what's outside our universe? Is it expanding? Why is it expanding? What is dark energy? What is dark matter? And why is the universe flat? Then we've got gravity. So we know that gravity is a force which is acting on mass to cause it to attract to other mass. We think that is because it's bending space-time. And so we want to know what gravity is. We want to know how it works. We want to know why it affects space-time. And then we also want to have an explanation for gravity rotation curves, an explanation for black holes, an explanation for gravity on a quantum mechanical level. And we also want to be able to incorporate that theory of gravity into the standard model. And then we've got light and electromagnetic waves, and we know that they all have the properties of waves, and we know that they travel through a vacuum, and we know that their speed is universally constant. So we want to know, what are electromagnetic waves? Are they particles? Are they waves? Are they wave-particle duality? Why can they travel through a vacuum? And why is the speed constant in a vacuum? And how is that possible on a logical and easy to understand explanation? Then we've got time, so we want to know what time is. We want to know why it's relative. We want to know why it changes due to our movement, and we want to know why it changes due to gravity. And then we have all the elements together, and we can see that they obviously follow the same rules. There is obviously some universal underlying physical principles that govern the universe and how it behaves. We can see that the universe behaves similarly in every direction, and so we want to know what those rules are, and we want to know why we haven't already got a single unified model. All right, so that's a lot to cover, and so we're going to do our best to cover that all today, and I'm going to try my best to answer every single one of these questions in this video. So obviously I'm not going to go and cover every topic. I'm not going to be covering every topic in a huge amount of detail because we just don't have time. This is going to be a brief summary that it gives us a model of how all these things fit together in a simple, easy to understand model, and answers every single one of these questions. So what do we need? We need to have our model be built on simple, sound principles. We need it all to be connected together. We want no exceptions whatsoever. If there are any exceptions, we're going to try and have a clear and easy, understandable reason for that exception. And we want this to be simple and easy to understand. So you might be thinking that's a big ask, especially in a random YouTube video. So hopefully you can bear with me, and once we get to the end, hopefully you'll agree that we've done all those things. All right. So where do we start? Let's go back to the universe and start with step one. So the universe, what do we need to know? We need to know, why is the mass evenly distributed? Why is the universe flat? Why is it expanding? Why is the expansion accelerating? And then how does the mass stay evenly distributed despite it moving and expanding? And then finally, is the universe infinite or is it finite? All right, so what else do we know that's expanding and remains evenly distributed? So this is a good analogy which a lot of physicists use. They use the old raisin bread. So if we imagine our universe as a dough full of raisins, then we can imagine that the galaxies in mass in our universe is those raisins, and we can imagine that as we put it in the oven and the dough expands, all those raisins move outwards. None of them are moving in the dough. They're all motionless inside the universe, but they're all moving apart from each other at equal and even rate. So they remain evenly distributed, but they all expand together. Okay, so here's a video I found on YouTube of some raisin bread. So this is our analogy of the universe. We can imagine that everything inside the bowl is our universe. That's the dough and the raisins. The raisins represent the galaxies in our universe. This dough represents the space. And as that dough expands, you can see that the galaxies remain motionless in its surrounding space, yet the space expands outwards, causing the universe to expand, and therefore the galaxies move apart from each other. But the galaxies aren't actually physically moving, they're suspended in the universe, and the universe expands, and the galaxies are incorporated in that. So another good example of a mass that remains evenly distributed throughout its volume as it contracts and expands is a gas. So here in this diagram, you can see that the mass of particles of gas are evenly distributed throughout its available volume. And as the volume changes, the pressure gradient changes and the mass remains evenly distributed throughout. So we can think of this as our universe. If space is a state of matter like a gas, then we can think of our universe as a single mass of space. And so if that single mass of space is in a small volume, then the space is evenly distributed. And as the volume of the universe expands, then the space in that universe, just like the gas, expands and remains evenly distributed, constantly reaching a new equilibrium. Okay, so let's go through these bullet points quickly. If we think of space in our universe as a state of matter, just like a gas, then we would expect that all the particles of space to be evenly distributed throughout its volume. We would expect that as the volume increases, then the particles would redistribute and remain evenly distributed. We would expect if we release this gas under pressure, then it would expand outwards due to a pressure gradient between the inside and outside until that pressure gradient reaches an equilibrium. And throughout that time, as the volume expands, the distribution of mass should remain evenly distributed throughout its volume. And so if we think of our universe as a single mass of space, and we think of space as a gas, then we can think of our universe as kind of like a cloud or a volume of gas. If that was the case, then we would expect that space would be evenly distributed throughout the volume of the universe. We would expect that any mass suspended in space would, like galaxies, stars, black holes, would be evenly distributed throughout the universe. And as the space redistributes and the mass floating in that space is redistributed, the mass would remain equally distributed as well. So all the galaxies would remain equally distributed as they're suspended in the floating space. So if the universe was a big cloud of space, then as the universe expands, the space in the universe would redistribute, and the mass in the universe, like the galaxies and stars, would remain roughly evenly distributed throughout as well. If space was a medium and the universe was a single mass of space, then this then if the space outside of our universe was less dense, we would expect the universe to accelerate outwards. We would also expect the mass of the universe to remain evenly distributed throughout its volume as it expanded. So this theory that the universe is a single mass of space and that space is a mass just like any other gas, then this would account for why the mass of the universe is evenly distributed and why the universe is expanding. We can then go on to say that space and mass would be evenly distributed throughout the volume of the universe. There would be a pressure gradient between the inside and outside of the universe, and this would cause the universe to expand. The space inside the universe would remain evenly distributed as it expanded, and therefore all the mass in the universe floating in space would also remain evenly distributed as well. As the universe expands, the pressure would remain and the expansion would continue to accelerate. So if we imagine that outside the universe there was no space or a true vacuum, then we can imagine outside the universe the pressure is zero. And so there's always going to be a constant pressure gradient between the positive pressure inside the universe and the zero pressure outside the universe. And therefore, as the universe expands, it will continue to have a force acting upon it, and therefore it would continue to accelerate. And as the pressure gradient decreases, the acceleration would decrease, but because there's always a pressure gradient, the acceleration would never reach zero. So we will always continue to accelerate if we take out factors like friction, gravity, lack of momentum and energy. So if space was a gas, then this would explain why the mass of the universe is evenly distributed. It would explain why the universe is expanding. It would explain why the expansion is accelerating, and therefore it would explain all the factors that we need for dark energy. And it would also explain how the mass of the universe can remain evenly distributed despite it constantly expanding at an accelerated rate. So now we go back to our analogy of raisin bread. It seems to make a lot more sense. We can think of the universe as a single mass. We can think of space in our universe as the dough holding the universe together, which behaves like a gas. And we can think of all the mass in our galaxy, like in our universe, like the galaxies and black holes and stars, as raisins floating in space. And as that space expands with the increasing volume of the universe, the mass floating or suspended in that space moves with the space suspended in it, not moving through the space, but suspended in space as it expands, and therefore it gives us the appearance that all these galaxies are moving apart when they're actually motionless in an expanding space. Okay, so that just leaves us with one last question about the universe, and that is the universe infinite or is it finite? And so by definition, according to this theory, the universe has to be finite, because if we think of the universe as a single mass of space, just like a single mass of gas, then in order for the universe to expand outwards and to continue to accelerate outwards, there needs to be a pressure gradient between the inside and outside of the universe. So in order for this theory to work, the universe must, by definition, be a finite mass, and so it cannot be infinite. But if we take away this theory and just think about it logically, then by definition, anything that is expanding cannot be infinite. So let me talk about this a little bit more. If we take an example, we imagine our balloon and we put our balloon inside a box, then we can expand our balloon. So just our volume of gas, we can expand this volume up until it completely fills the volume of the box. So if we then had infinite boxes, so then we can think of each box as being completely surrounded by boxes on every side. And so if every single box was surrounded by other boxes in infinite different directions, then as any single balloon expanded outwards, it would be impossible for that balloon to expand outside the perimeter of its own box. And if it did so, it would then expand into another box. And if every box had an equally sized expanding balloon, it would be impossible for any of the balloons to expand anymore. Even if you removed all the boxes, the entire volume would be completely consumed, and so it would be impossible for an infinite volume to expand any further. Let's think about that in the way of the universe. So we had a map of our universe, and we saw that all the galaxies in our universe are roughly evenly distributed. We could put an imaginary grid into our universe, and of every volume of space or every part of the universe that was inside that grid expanded, then it would be impossible for any volume inside any grid to expand outside of its own grid without it expanding into another grid. And so even though these are just imaginary hypothetical grid lines or markers on a map, we can imagine that of any volume of space or gas or the universe was expanding, then in order for it to expand, by definition, it must expand outside its own perimeter and into the perimeter of another galaxy or volume or space or gas. And so if every single area was surrounded by another area on every side, it would be impossible for any volume to expand outside without interfering with another one. So by definition, any infinite volume can no longer expand. And so the fact that the universe is expanding in itself is proof that it cannot be infinite, because if it was infinite, it would have no available volume to expand into. So therefore, it is impossible for an infinite volume to increase. Therefore, the universe must be finite, or it would be impossible for it to expand any further. So let's summarize this for the universe. So we have a number of questions that we wanted to answer at the beginning of this topic. We wanted to know, why is the mass evenly distributed? Why is it expanding? Why is it accelerating? How does it remain evenly distributed? And is it finite or infinite? And so now we can answer all those questions simply and logically. We can say that the universe is a single mass of space, that space is a mass which behaves like a gas. And so just like any other gas in any other volume, the mass of the universe is evenly distributed throughout its available volume. If the pressure gradient between the inside of the universe and the outside of the universe remains, then the volume of the universe will expand outwards due to that pressure gradient. If there is no pressure outside the universe, then there will always be a pressure gradient, and the universe will continue to expand until it's reached an equilibrium where the pressure gradient is equal between the inside and outside. And while it is expanding, the space inside our universe will behave like a gas, and so will remain evenly distributed throughout its available volume. If all the mass in our universe is evenly distributed through space, then as the space expands, the mass in our universe will remain evenly distributed. And in order for our universe to be expanding, it must, by definition, be infinite. Okay, so we've covered the universe. What's next on our list? We're going to cover some topics on gravity. So what's our questions for gravity? We want to know what gravity is. We want to know how it bends space-time. We want to know how that works with dark matter and what dark matter is. And we want to know, how does gravity work on a particle level? So let's see if we can cover these off. Okay, so the theory of gravity so far, we've got general relativity. So Einstein came up with the concept that there's 3 dimensions in space, and then there's a 4th dimension in time. So this comes up with a 4-dimensional theory of space-time. And his concept of gravity is that mass somehow bends space-time, and that curvature of space-time results in the effects of gravity. Okay, so let's cover that very quickly. So why do objects orbit each other? So we have here mass, and that mass is bending the fabric of space-time. And so if an object is passing by that mass at exactly the right angle, at exactly the right distance from that mass, at exactly the right speed, and at exactly the right time, then if everything lines up perfectly, theoretically, we can get that object to orbit that mass. And so that's our explanation for how gravity works, and for why all the objects in our universe, like the moon orbiting the Earth orbiting the sun, and then every star in the galaxy orbiting the galaxy, is put down to this principle. So we can kind of make sense of that. So we can imagine that, hey, there may have been hundreds, thousands, millions of planets that were shooting past through space at just the right time, multiple collisions, lots got lost into the sun, lots got shot off into space, and then uh, out of almost what seems like a miracle, about 8 or 9 planets end up going at exactly the right speed, exactly the right time, exactly the right distance, exactly the right angle, and just everything seems to line up perfectly. And that's how we created our solar system. So we can imagine that of the millions of planets that shot past our sun, 8 or 9 of them ended up orbiting our sun perfectly, and the rest collided or got destroyed or shot off somewhere else. And so we can theoretically contemplate general relativity, and make a little bit of sense about it. So that would make sense on on a solar system level, but what about on a galaxy level where we've got something like 100 million stars all perfectly orbiting at exactly the right speed, all different speeds, exactly the right distance, all different distances, exactly the right angle at exactly the right time. So it almost seems like an absolute miracle that something as intricate and as stunning as a galaxy can come to be from absolute chaos. And then when you look at the universe and we see there's something like 2 trillion visible galaxies, this becomes beyond a miracle that this can happen exactly right 2 trillion times in a row. And it's amazing that the entire universe isn't just a cluster of stars and galaxies and everything shooting in every different direction. So here, if we imagine that the central mass is something like the mass of our sun, and that this sheet is the curvature of space-time, and you can see that this mass curves the curvature of space-time. So we throw multiple different objects in multiple different directions, then some of them fall off the sides, some of them collide into the sun, a lot of them collide with each other, and then ultimately, after a short period of time, we're left with a few orbiting objects perfectly orbiting the Earth or the sun. And so we've got to start with a whole collection, and then we're down to a few. And so this is a good way of representing how something like our solar system works, where we've got several planets that just happen to perfectly orbit the sun. But what about something like our galaxy, where we've got 100 billion? Does that still make sense? Okay, so what is wrong with general relativity then? Well, it seems to work in concept and it makes intuitive sense, but what happens when we run the numbers and we apply this to real world situations? So uh, let's look at how much curvature it takes for something, say, the Earth. So it's difficult to compare space and time because they're 2 different metrics, and so you can't directly compare minutes and seconds and hours with meters and kilometers and light years. And so there's no direct comparison between time and space that we can compare to. What we can compare, though, is a gradient, so a change in time or a change in distance. And that we can kind of conceptualize a little bit easier. So the way I look at it is that we can see a gradient in space. So we can see a gradient on a hill. And so, for example, if we're looking at this example here, we can say that, well, the height between the edge of the sheet and the central mass is approximately 1, then the distance out is probably 2 or 3 or maybe 4. So we could say that the gradient here is a probably 1 in 3 gradient, where it drops 1 for every 3 it goes along. And so we can see that a change or an angle is something that we can compare or make relatively good comparisons to something like time, which is a completely separate unit which can't be directly comparable. So if we looked at the gradient of change in time as or change in space-time, then we can compare that a little bit better. So let's do the maths for Earth. So what is the curvature of space between something that is in 0 gravity, say 100 or 200 or 1,000 kilometers outside of Earth, to the curvature due to the mass of the Earth on the surface of the Earth? And so if we crunch the numbers and we use general relativity as a rough approximation, we can say that for every 30 million seconds in zero gravity, we lose approximately 1 second on Earth. So we can say the gradient or the slope or the change in space-time between an area of zero gravity and the surface of the Earth is that we lose 1 second for every 30 million seconds, or 1 year for every 30 million years. And so then we can compare that to our example of curvature of space-time where we imagine if the gradient of this curvature was 1 in 30 million, would that be enough for the orbit, for these objects to orbit a mass? And so it seems unlikely given how flat that is. Another way you can conceptualize curvature of space-time and gravity is imagine that that mass was the Earth. Imagine that that marble was an object or a rocket or a person that was trying to jump off the surface of the Earth. And so if a person jumps and the gradient here is about 45 degrees or 30 degrees, then you can see that they would quickly fall back down to Earth. They'd be pulled back in by the curvature of space-time to cause gravity. But if we think of the gradient of curvature of space-time on the surface of the Earth is now 1 in 30 million, and someone jumped, then do you think a gradient of 1 in 30 million would be enough to stop that person a foot from the ground and pull them back to the surface of the Earth? Or would that be not a significant enough gradient, and perhaps we'd end up shooting off into space? So again, the general theory of relativity makes intuitive sense when we look at it as a curved sheet, but when we crunch the numbers, it may be enough to catch a few balls to cause our solar system, the planets in our solar system, to orbit, or it may be enough to cause a ball to fall into a sheet, but it doesn't seem like it's enough to catch 100 million stars in a galaxy, and it doesn't seem like it's enough to stop us from jumping off the surface of the Earth. Okay, so do we have a better explanation for what gravity could be? So let's do a thought experiment. So this is number 2. What if space was a medium, which we've already covered, that objects were floating in space, and that mass itself consumed space, so that gravity was the movement and direction of space at any given point of time? And so gravity is the movement of space, and mass consumes space, so anything suspended in space would move due to the consumption of space. Let's explore this idea a little bit further. Okay, so let's look at this video as an example. So let's imagine that space is a medium, just like the water in this bucket, and that these objects are the objects in space, which can be stars or galaxies or the planets in our solar system. And then the hole in this bucket is effectively the central mass. So that can be the star in our solar system or the center of our galaxy. And so that central mass is consuming the medium of space. And then any objects floating in that space therefore move suspended motionless in the medium. And so let's have a look at these balls. So as you can see, these balls aren't chaotic. They're not shooting in different directions at different times at different speeds. They're all just motionless, floating in the water that they're suspended in. And automatically they go to the correct speed, at the correct angle, at the correct movement, that they all orbit perfectly. And so we can see here that this perfectly represents any central mass in our galaxy or our solar system or in our universe as a mass that is consuming the surrounding medium of space, and the objects suspended in that space may therefore begin to orbit perfectly, not needing initial movement or direction or timing, but just suspended, floating, motionless in space, and then automatically move in the right direction at the right speed at the right time for their position relative to that mass. So now when we look at something like a spiral galaxy in our universe, it almost becomes clear and obvious that this looks like the whirlpool in our diagram. You can see we've got a central mass which is consuming the space around it, and as it consumes the space around it, then that mass and the stars and all the rest of the galaxy end up orbiting that galaxy as they are floating suspended in space as that space is consumed by the central mass. And so these stars don't need to be heading in random directions at different speeds, at different times, at different angles, and all just happen to perfectly suit up. They just sit there floating motionless, and the consumption of the space from the central mass causes the whirlpool, which pulls in all that surrounding mass. And all that surrounding mass ends up naturally going to the exact right angle, velocity, and distance from that mass as it is drawn in by the surrounding space. Okay, so now we can hypothesize that gravity is the movement and direction of space at any given point. So we have a theory for what it could be. Does the theory fit the maths? Does this work in the real world? So let's figure that out. So let's start with the basics. If we were imagining water traveling through a tap, then we can tell the velocity of that water by taking the volume that passes through that tap every second and dividing it by the surface area that it passes through. So if we're thinking that gravity is the movement of space, we want to know the velocity that space is moving, and that should be equal to the force of gravity. How do we figure that out? Well, if we've got a pipe, then we can see that the velocity that the water is moving through the pipe is equal to the total volume of water that passes through that pipe every second. We can calculate that by taking the total volume. We can take the surface area of the pipe and the velocity of the pipe to calculate the total volume. If we were doing something like mass in space or the Earth or the Sun, then we can take the total volume of space that is consumed by the total mass, and we can work out this surface area that volume has to travel through to work out the velocity. And so if we take the point of the surface of the Earth and we work out the surface area of the Earth, then the total volume of space divided by the surface area of the Earth must equal the velocity or the force of gravity. Let's work that out. So first of all, we need to know how much volume of space is consumed by mass. So we want to work out the volume of space consumed per kilogram per second, and I've just labeled that as Vx. So if we know the density of the space is constant, we know that mass consumes space at a constant rate, and if we assume that mass consumes space evenly in all directions, then we could calculate the volume of space consumed per kilogram of mass by every second. We can also calculate the surface area of any point that space must travel through to reach that mass as the surface area of a sphere. Therefore, we can calculate the velocity and direction of space at any given point if we know the volume of space consumed, the mass consuming it, and the surface area from where we're measuring it from. So, therefore, gravity or velocity of space, so the gravity equals the velocity and direction of space. So we can calculate the force of gravity using the formula velocity equals the volume of space consumed divided by the surface area it must travel through, which can be altered to gravity equals the volume of space consumed per second divided by the surface area that space must travel through at any given point. As the space is consumed equally from all directions, the surface area would be the surface area of a sphere, where the radius is the distance from the point to the center of the mass. And so we can come up with the formula gravity equals the velocity, the volume of space consumed per kilogram times the amount of kilograms of the mass divided by the surface area of the sphere. Okay, so this is our formula. Gravity, or the velocity of space, equals the total volume of space consumed by any given mass divided by the surface area of a sphere, where the distance is the distance to the center of the mass. So we can rearrange that formula. We know, let's go back. We know the force of gravity on Earth. We know the mass of the Earth, and we know the radius of the Earth So we can take all these variables, and the only one we don't know is the volume of space consumed per kilogram per second. And so we can rearrange this formula to find out what Vx is. And so if we rearrange that formula, we find that Vx equals 4 pi r squared times gravity divided by mass. We can then take the objects in our solar system, including the Earth, the Moon, and all our planets. We know the mass, we know the gravity, we know the radius, and we convert that to find Vx. We can see that it's fairly consistent on Mercury, Venus, Earth, the Moon, Mars, and all the other planets in our solar system. The volume of space consumed per kilogram per second is around about 8.4 to the negative 10. We can also derive Vx using Newton's formula for gravity, or the gravitational constant. So we know that Newton's formula for gravity is gravity equals the gravitational constant times the mass divided by the radius squared. Our formula for gravity is Vx times the mass, 4 pi r squared. And so we can combine these two formulas to see that Vx is just 4 pi times the gravitational constant, which ends up being 8.39 to the negative 10 meters cubed per kilogram per second. Okay, so that gives us Newton's formula, which isn't much different to what we already have, apart from giving us an explanation for what the gravitational constant actually is. And the gravitational constant, according to this theory, is just a fraction of the volume of space consumed per kilogram per second. But what about the force of gravity in a galaxy? Well, we know a single spherical object consumes space from all directions, and we can use the distribution of space as the surface area of a sphere. Then maybe a galaxy consumes space differently, as a galaxy isn't in the shape of a sphere. Maybe a galaxy consumes space in a way that is related to the shape of the galaxy itself. So as many of the galaxies are shaped in the shape of a disk, then maybe they consume space in the shape of a disk as well. So let's test this hypothesis out. If we know that the force of gravity is equal to the volume of space consumed by a mass divided by the surface area in which it's consumed, then all we need to do is take out the surface area of a sphere and replace it with the surface area of a disk. So gravity equals the movement and direction of space in any given location. Mass consumes space, creating a force of gravity, and gravity is equal to the volume of space consumed per second divided by the surface area in which it is consumed. So let's change the surface area from a sphere to the surface area of a disk. So therefore we'll have gravity equals the volume of space consumed by the mass divided by the surface area which it travels through, in this case the surface area of a sphere for a disk for a galaxy. So this gives us the formula gravity equals Vxm divided by the surface area of a disk, 2 pi rh. Well, we already know the force of gravity, we already know Vx, we already know mass, and we already know radius, so we can rearrange this formula to find out the height, and we can test that against our data sets. So here is the data sets for a number of galaxies where we're working out the height. And as you can see that the height of these disks usually starts small, builds up, and then plateaus out. And if you compare this to the total mass of those galaxies, you find that this is actually very similar. So what I've done next is divided the height by the total visible mass of each galaxy. And here you can see that most of these lines plateau out to form a nice straight constant. So there's some constant for each of these galaxies, which is equal to height divided by the mass. And if we play around with the numbers a little bit, we can see that height is roughly equal to square root 2 times the visible mass, and that gives us a rough constant of about 1 for most galaxies. Another way of displaying that was to say that mass is equal to half the height squared. So we can rearrange that formula as well. But if we use this as a general rule of thumb for the height of each individual galaxy, then we can put that into our formula and see how the numbers work. So gravity equals the volume of space consumed by the mass given this divided by the surface area in which it is consumed. And for a galaxy, the gravity equals the volume of space consumed by that mass divided by the surface area of a disk. And so we can work out the height of that disk as equal to square root 2 times the visible mass, and that gives us the formula gravity equals the volume of space consumed by that mass divided by the surface area of a disk, with which is 2 pi r square root 2 times the visible mass. Let's put the numbers into some charts and see what they look like. There's a whole bunch of equations that I'm not going to go into. If you want interested in maths, you can pause these videos and look at what I've written, but it's all pretty dry. Probably the most important thing here is I've just simplified it down, taking out all the constants into making it an x. So you can see that currently the volume of space consumed per second is a constant, although that does change, so it's not actually a constant, but for the purposes of this video, it is divided by 2, square root of 2, and pi, which are all constants. So we can make all those constants x. And then if we want to find gravity, we can times x by the square root of the mass divided by r. Or if we want to find mass, we can times gravity by the radius divided by x squared. So we punch those numbers in and see what they show up with each galaxy. So here we have galaxy hash N2403. The blue line here is what we've calculated gravity to be given the observable mass. So we've taken all the visible mass that we can see in that galaxy. We have calculated the force of gravity from that mass using the equations previously, and then we can compare that to the observed force of gravity here, and you can see that that works pretty well. So that's one galaxy. If we look at more, we can see hash N1003, also very accurate. We've got M33 is accurate. We've got more that are pretty good, and we can just keep going. And it looks like it works for most galaxies that I've tested. And so you can pause this video and look at them closer. But we can find that if we're calculating the force of gravity for any galaxy, then it works pretty well to these formulas. What do we want to calculate? Orbital velocity. That's going to be pretty relevant because the two things we can see in any galaxy is the mass of that galaxy and the orbital velocity of the mass in that galaxy. So we can calculate the mass of that galaxy using the orbital velocity, or we can use the orbital velocity. We can calculate the orbital velocity using the mass, and the mass using the orbital velocity using this formula here. So let's test that out as well. Here we have galaxy DDO154. Again, you can see that the calculated orbital velocity is the blue line, the observed orbital velocity is the red line, and you can see that these match up pretty similar. So for this galaxy, that formula works pretty well. We can also see it for this one, and so on. If we want to calculate the mass using the orbital velocity, we can rearrange the same formula, and we can see that they all work pretty well. And there's lots of examples. So what have I done? What have I been showing you? I've been showing you that we can calculate the orbital velocity and galaxy rotation curves from visible matter alone. Therefore, the primary evidence for dark matter is the discrepancy between our understanding of gravity and the orbital velocity of galaxy rotation curves. And using this theory for gravity and these equations, we can effectively eliminate the need for dark matter by demonstrating that we can predict the orbital velocities very accurately with visible matter alone. Therefore, we do not need dark matter to account for the gravitational rotation curves, and therefore our current understanding of gravity is incorrect, and dark matter in itself may not actually exist. So what evidence is there for dark matter? Well, it's not just gravity rotation curves. There's also things like gravitational lensing, galaxy collisions, and variations in the cosmic microwave background radiation. So now if we think of space as a medium, like a gas, and we think of gravity as the consumption of space by mass, and the fact that galaxies consume space differently to single individual objects, then we can account for galaxy rotation curves, therefore accounting for the primary evidence for dark matter. gravitational lensing, again, I haven't gone into light yet, and we'll talk about that more in this video, but we can assume that if light is a wave and space is a medium, then as we warp and move and manipulate space, we can manipulate the light that travels through it. And therefore, we will be able to account for gravitational lensing using these theories. Galactic collisions is one of my favorites because I like to think of space as a cloud or as a mass. So if you imagine that galaxies are clouds of space with mass in them, then when they collide, this creates eddy currents, this creates turbulence, this creates movement in the space, and so that can account for galaxy collisions as well. So we can think of the air around a jet as a jet comes into land. The moving air impacts the motionless air, and you get these eddy currents and this turbulence that comes off the jet. And you can think of galaxies as the same. You've got a moving galaxy hitting a galaxy which is moving at different speeds or different directions, and the space around those galaxies creates eddy currents and turbulence as they collide. And then again, variations in cosmic microwave background radiation. Well, now that we think of space as a mass, we can think of cosmic microwave background radiation not as the remnants of the Big Bang, but actually the energy dissipated by the energy of space. And so space itself has mass, space itself has energy, and we see that energy in the form of cosmic microwave background radiation. And so now we can think of space in our universe just like the air in our atmosphere. It can have its own pressures, its own temperatures, its own movement and direction. We can have a little microclimate. We can have different weather patterns. We can have cyclones and tornadoes and all the things we have in our weather. We can also expect to see that in our galaxy. And so we can see those variations in cosmic microwave background radiation as variations in the energy in space, or the movement in space, or the temperature of space. And so this all fits perfectly into our theory, giving us an explanation of all the phenomenon of dark matter. Okay, so let's summarize gravity and see if we've answered all our questions. So we want to know what gravity is, we want to know what in space-time, we want to know what dark matter is, and we want to know how gravity works on a particle level. So what is gravity? Well, we now think that gravity could be the movement of space. So at any given point or location, space can be moving at a set velocity in a set direction. We know that mass consumes space, and therefore that as it consumes space, it causes the movement of space, and we can calculate the force of gravity by the amount of space consumed and how it's distributed. How does gravity bend space-time? Well, gravity doesn't bend space-time, it moves space, and so it doesn't bend it, and that bends space and not time. So potentially here we can extract time out of the space-time concept and look at them as individual entities, and we'll come back to that later when we discuss time. What about dark matter? What is dark matter? Well, we can now see that dark matter is the distribution of gravity in a different way. So if an individual mass consumes space from all directions, then the effect of dark matter or gravitational rotation curves are displayed as a different distribution of how we're consuming space around a galaxy. How does gravity work on a particle level? Well, we think that mass is consuming space, so let's explore a little bit more about that on an individual particle level. So why does mass consume space? Well, to really understand this, I want to kind of go back to the basics. So I'm going to cover the laws of thermodynamics. So the laws of thermodynamics, there's three main laws. One, energy cannot be created or destroyed. Two, that entropy is always increasing. And then three, the entropy of an isolated system approaches a constant value as the temperature reaches absolute zero. Why is this relevant? Why am I talking about this? Well, if we look at Einstein's theory that mass is equivalent to energy, or mass and energy are equal, and we look at the laws of thermodynamics, then all objects will gradually lose usable energy over time, and nothing has perpetual energy, therefore nothing can last forever. And if these are true laws, then there shouldn't be any exception to this. So what about our universe? Well, our universe is made up of mass and energy. And the universe is approximately 13.7, 13.8 billion years old. And usable energy is constantly being lost due to entropy. So if mass is energy, then is our universe losing mass? And I don't think it is. So why is that? Let's look into that. So to understand that, we need to stand mass on a particle level. So let's look at the basic building blocks. Let's start with the atom. If we look at an atom and we go over the very basics, we can see that the visible mass of our universe is made up of atoms, and 98% of the visible mass of our universe is made up of hydrogen and helium. The mass of a hydrogen atom is approximately 0.16 billionths of a joule. A hydrogen atom or any particular atom in our universe is constantly moving, it's constantly vibrating, it's constantly colliding, it's constantly dissipating thermal energy. So they should be constantly losing thermal and kinetic energy. And if our universe is 13.8 billion years old, then why does all the mass of our universe still have the exact same amount of energy as it did when it first began? So why each individual hydrogen atom still have the same 0.16 billionths of a joule that it started with 13.8 billion years, when it's been constantly moving, vibrating, colliding, and theoretically should be losing some form of energy in some way or another. So this is our first problem. If the laws of thermodynamics state that everything loses energy over time and that nothing lasts forever and that there's no such thing as perpetual motion, then how are the atoms in our universe constantly moving, vibrating, colliding, and yet have never lost any mass energy? Okay, so we have two possible explanations for what's going on here. Either atoms and mass in our universe have infinite energy and last forever, or the atoms in our universe are getting energy from somewhere else. And if that is the case, then where are they getting energy from and how are they getting it? Okay, so in order to answer that, we need to go back to the basic fundamental building blocks of an atom. And so see what we understand. So an atom is made up of protons, neutrons, and electrons. The protons and neutrons make up the nucleus, and this is the vast majority of the mass of the atom, but it's only a very small fraction of the volume of the atom. On the flip side, you've got the electron, and so the electrons are a very, very small part of the mass of the electron, of the atom, but they can show up anywhere in the electron cloud. And the electron cloud takes up the vast majority of the volume of the atom. So inside the electron cloud, we don't know exactly where that electron is going to be at any point in time, and we don't know exactly where it's going. It is traveling constantly at about 2,200 kilometers per second, and it's been doing that for the last 13.8 billion years. So where's all that energy coming from in order to keep an electron moving constantly at 2,200 kilometers per second for the last 13.8 billion years? Well, in order to answer that question, let's break down the individual parts of the atom. So if we look at the half-life of a hydrogen atom, then we effectively classify it as stable, which means it almost lives forever. If we look at a proton on its own, then that is also stable. And if we look at an electron on its own, then that's stable. So all of these components individually on their own live forever. They have perpetual motion and perpetual energy. If we look at the neutron, however, and we isolate an individual neutron on its own, then we see that it has a half-life of about 10 minutes, which means it spontaneously decays in about 10 minutes on its own. So why does it do that when the hydrogen atom, the proton, and the electron are all stable? And in fact, if we look at a neutron when it's attached to a proton, then it automatically becomes stable and has a perpetual lifetime as well. So there's something about that proton that's giving the neutron longevity to last forever. So that brings me to another hypothesis. One, that mass is consuming energy constantly, and two, that atoms are consuming electrons to get their energy, and without electrons, an atom or mass would decay. So let's look into that a little bit more. So let's theorize, what if atoms and all the mass must consume external energy or they will decay? The electron, which we see attached to an atom, is not in fact a single electron, but is actually a constant stream of electrons being caught and consumed by the atom as an external energy source. So if that is the case, then where are all these electrons coming from? Well, we know that mass is everywhere throughout our universe, and so in order for mass to continue to survive and not spontaneously decay, then electrons must be also distributed throughout our entire universe. And so we can hypothesize that perhaps space is actually full of free neutral electrons. And that these electrons are distributed evenly throughout our universe in space. Then electrons could be the particles that make up the medium of space. Okay, so what if protons use their positive charge to catch an electron? And so once an electron has been caught by a proton, then it generates a negative charge. And so we see the electron when it's caught and we see that it has a negative charge, but what we're not looking for is all those remaining free electrons, which we're not detecting because they don't create their own positive charge. And so neutrons must be attached to a proton in order to receive energy. And if they're not attached, then they will quickly decay within 10 minutes because they have no external source of energy. Okay, so that's a lot to take in, and I know it's a bit of a long shot, but if you want to learn more about that, you're welcome to read my book, GOM, which there's a link to available. But effectively, if we can summarize this now, then our new theory of gravity, we can look at, we can incorporate gravity into every single level. So we can understand gravity through individual objects like us on Earth, our moon, our planets, our solar system, our stars, as mass consuming space from every direction. Therefore, we can calculate the force of gravity as the surface area of a sphere. We can see that the larger masses in the universe, like galaxies and galaxy clusters, consume space in different distributions. So we can also understand how gravity works on galaxies and galaxy rotation curves. We can also help understand galaxy clusters and collisions, galaxy fragments, and the structure of the universe as a whole as being an enormous single massive space, and how that space is consumed by mass just then determines how the forces of gravity play out throughout our universe. Not only can we see it on the large scale, but we can also now understand it on an individual particle scale. So we can understand that the force of gravity is electrons being consumed by atoms for energy, and that consumption of those electrons in space is therefore causing the effect of gravity. So we can understand gravity on a particle level, we can understand gravity on a galaxy level, and we can now understand dark matter, dark energy, and we can put all these elements together. So we have a standard model of the universe. This model is currently missing three main elements: dark matter, dark energy, and gravity on a particle level. And so now that we have the final missing pieces to that standard model, hopefully we'll be able to incorporate this into the standard model and create a final theory of everything, which would be a good thing. Boom. Okay, how's your brain cell feeling? I'm sure it's hurting at the moment, so there's a lot to take in, and we covered a lot. I know it's very controversial. It's nothing like our current theories, but as I said before, we're looking to have a simple, easy to understand, all incorporated theory that incorporates all the different elements of our universe. And so far we've incorporated the universe on a grand scale. We've talked about gravity, we've talked about dark energy, we've talked about dark matter. what else have we got to do? Well, we still have to cover light and time. And so I know you're probably bored out of your mind right now, so I'm going to try and make this as quick as possible and wrap this up. So we'll go pretty quickly through this. All right, so light, what do we want to know about light? We want to know whether light is a wave or a particle or wave-particle duality or both, or what's going on there. We also want to know how light can travel through a vacuum, and we want to know how and why it is possible for light to the speed of light to always remain constant, irrespective of movement. So yes, we understand it does that, but how does it do that? What's the explanation for it? Okay, so is light a wave or a particle? Well, if we look at light on Earth outside of a vacuum and working through a medium, then we can very clearly say that light is a mechanical wave. So light on Earth traveling through air, water, glass, plastic has all the properties of a mechanical wave. We can say it's got a wavelength, a crest, a trough, an amplitude, a frequency. It has all the characteristics that we would expect to see in a mechanical wave. We also see that it has the properties of refraction, reflection, interference, diffraction, and absorption. So if we exclude the scenario of light traveling through a vacuum, we can say that light is 100% a mechanical wave. So why do we have doubts about it being a wave? Well, because it can travel through a vacuum and it shows properties of a particle. So if we expect space to be a medium or a state of matter like a gas, then we can say that light isn't traveling through a vacuum, it's still traveling through the medium of space, therefore taking away the first factor, which makes us question whether it is a wave or not. Then we can say that all light and all electromagnetic waves are waves traveling through particles in space. So that just brings us to the next question. How and why is the speed of light universally constant through a vacuum? And so if everything in space is moving, then why is the speed of light constant? So we expect that we're on Earth and the Earth is moving relative to the sun and the sun is moving relative to the galaxy and the galaxy is moving relative to the universe. How do we get the speed of light to always reach us on Earth at a constant rate? And the answer to this is that we are measuring all light from Earth. And so if Earth is motionless in surrounding space, then as a wave travels through a constant medium, it will always reach a stationary source traveling at a constant velocity. Therefore, as all waves on Earth reach Earth from space, they will always be traveling at a constant speed. So I know this is a little bit hard to comprehend at first, so let's just go over it a little bit more. So let's go back to our example of space being a medium, just like water, and that the balls are objects in space, floating in space. So we imagine our solar system as the center of the whirlpool is our sun. So the hole in this bucket is the sun consuming space, and the water in this bucket is the space around the sun. Then we can imagine that the balls in the water are the objects in our solar system. And as you can see, the balls themselves are not moving relative to the water that they are floating in. So the balls are motionless in the surrounding space. And as the space moves and is consumed by the central mass, the planets in our solar system orbit motionlessly in the surrounding space. So if we're thinking of one of these balls as the Earth, then that ball is not moving relative to the water it is suspended in. Therefore, any light traveling through that water or any waves traveling through that water will reach the Earth at a constant speed. So going back to the water example, you can clearly see the similarities between a whirlpool of water and our solar system or a galaxy. And so every time you pull the plug in the bath or the sink and you see that water whirlpool down the drain, you can think of our solar system and you can think of a galaxy. All right, so you still don't believe me? Well, let's look at a specific example just to make this point clear. So one very fascinating star is called Mira. It's a variable star. It's in our galaxy. And the interesting things about Mira is that it is moving separately to all the other neighboring stars in our galaxy. This star seems to be moving in its own direction, in its own trajectory. And so, unlike all the other stars in our galaxy, which are all moving as they orbit the center of the galaxy, Mira seems to be cutting straight through it. And why is this interesting? Well, it's because of the features that Mira shows. So Mira has a number of unique features which are uh, uh, unique to this star. And as you can see, Mira has a tail and a bow shock and streams, and it has turbulence running off it. So why does Mira have a tail and a bow shock and turbulence running off it? Why is this star different to all other stars? And the explanation is that Mira is moving through space and not suspended in space. And so again, we can go back to our analogy of water and a boat. We can see that if we had a boat sitting floating in the water, then it wouldn't have a bow shock. It wouldn't have a tail, and it wouldn't create these eddy currents or turbulence coming off the back. And so we can clearly see the comparison between a boat traveling through the water and Mira traveling through space, creating a tail, a bow shock, and turbulence and eddy currents off the side as it travels through space. So I should mention that Mira is traveling no faster than our own sun through our galaxy, and yet our own sun and all other stars in our galaxy don't have these same features. So this is a good example of what we'd expect to see if we had a star traveling through space as opposed to motionless in space. And so you can now imagine that Mira does not have the speed of light reach it at all from all directions at a constant rate, because Mira is not motionless in a constant medium. And so as Mira moves forward, it would see that the light coming towards it was actually traveling faster, and that the light it was traveling away from was actually traveling slower, purely because of the Doppler effect. And the reason we on Earth always measure the speed of light as constant is because we are motionless in space, not moving through it, but suspended in it as it moves. All right, so this brings me to my big controversial hypothesis that the speed of light is not actually constant. The speed of light appears constant because it is always constant when we measure it motionless in Earth. And that is because we are not moving in our surrounding space, and the density or the optical density of space is constant around Earth. And so this is a very difficult concept for people to understand, especially when they've spent a lifetime learning that the speed of light is constant. And so to go into a little bit more detail, I'm going to use Einstein's very own thought experiment for relativity to set an example. So if we're looking at Einstein's theory of general relativity, or his theory of relativity at all, then one of the most fundamental principles of Einstein's theory is that the speed of light is constant for all observers. And in his explanation, he used a thought experiment, which was to demonstrate a light clock. And so I'm assuming most of you have heard of the light clock concept before, but here you can see that there's two light clocks. There's one on a stationary observer on Earth, and the light is bouncing from the top to the bottom and back up again. And each time it goes up and down, it measures time. And so then we have another identical light clock on a moving rocket. And as we can see, the speed of light is traveling at the same speed for both the person on Earth and the person on the rocket. But as we can also see, the clock on Earth travels travels faster than the moving clock in space on the rocket. And so we can say that due to Einstein's theory of relativity, that the speed of light is constant for all observers, yet we can observe things like time dilation or length contraction due to a moving observer. And so this is important. Why is this important? Well, if we move on and think of something like a black hole, then when we observe light near a black hole, we physically observe the light to bend towards that black hole, and we physically observe that light to slow down. So at the point of the event horizon, the light has physically stopped. So we may justify this saying that there's been time dilation or length contraction, but what we are physically seeing is motionless light. So if we go back to Einstein's theory or his specific example, we can see here that Einstein said that the speed of light is constant for all observers. So if you're on Earth and you're looking at the speed of light on your light clock, it's the same speed as the moving clock on the rocket ship. And so it has we are physically observing the speed of light to be constant for all observers. If we're looking at the light around a black hole, it has physically slowed down. It is not traveling at the same speed for all observers. We can see length contraction and time dilation on the rocket. We can see length contraction and time dilation around a black hole, but the underlying principle is that the speed of light should appear constant, and it does not. If I'm going to be pedantic and pick Einstein's theory out a little bit more, we can also look at it from the perspective of the rocket ship. So according to Einstein's theory, the observer on the rocket ship should see his light traveling at the same speed as the light on Earth. But if you can see here, the observer on the rocket ship actually sees his light traveling slower than the light on Earth. And so as this rocket ship observes the clock on Earth, he would observe the time to be traveling faster, and he would physically observe the light traveling faster as it's not moving through that medium. And again, this directly contradicts Einstein's theory of relativity, because according to Einstein, the observer on the rocket ship should see the light on Earth traveling at the same speed, where it's not, it's traveling faster, and he should see the clock on Earth traveling slower, and yet again it's not, it's actually traveling faster. So this is 2 points against Einstein's theory of relativity using his own example of general relativity. But the most important one is that if we're looking at a black hole, we should see light traveling at a constant speed relative to us, and we should not physically observe the speed of light to slow down. Okay, so this is all theoretical currently. So how can I prove that the speed of light is constant in the universe, and the real universe, as opposed to a thought experiment? So in order to do that, we can think about the redshift. So we know the universe is expanding due to the observed redshift that we see from the light from distant stars and galaxies. If objects in the universe are not moving through space, and in fact, we can think of space as expanding, like the dough in raisin bread, and that the raisins in the raisin bread aren't actually physically moving relative to the surrounding space, then if we take the fact that space is expanding, as the space expands, we would expect the wavelengths to get longer. We also know that if a wave is traveling through a medium, then the frequency of that wave remains constant despite the density or optical density of that medium. And so as the space expands, the frequency of light will remain the same, and the velocity and the wavelength will change. So as we know the frequency stays the same, and we can see redshift and a change in wavelength, then there must also be a corresponding change in velocity for the light. And so as wavelength increases, the velocity of light increases as well. And we can actually plot this on a graph. So here's a graph I took off the internet. This shows the velocity of objects in space moving away from Earth relative to their distance. And so we know, because of the redshift, that the further away an object is in space, the faster it's moving away from us. But if we then change our way of thinking to think that we're not moving through space and that space is expanding, then using that redshift, we can say that the change in velocity is actually the change in velocity of light traveling through the medium. So the further away an object is, the further back in time we're seeing it, the slower the speed of light. And so using the redshift, we can calculate the velocity that we are moving away from an object. The further the distance, the faster the velocity. And if we are not moving relative to the medium of space, then the change in velocity must be the change in velocity of light as space expands. So then we can take this graph and we can flip it around to look at the velocity of light over time. And so you can see on this graph that over the time period of the universe, we can see that the speed of light has constantly been changing at a pretty steady rate. Now, I have to say that I've only taken the data from the above graph here, which only goes back the last 2 billion light years or 2 billion years. And so our age of the universe is currently thought to be about 13.8 billion years. So I've only taken a small fraction of that and I've extrapolated it in a straight line. But as you can see from this graph, that the speed of light would have reached zero at around about 15.8 billion years ago, which is not what we initially thought, which is we calculated the life of the universe to be about 13.8 billion years old. So this could potentially alter or change what we think about the beginning of the universe. And again, this may not have been the beginning of the universe. This was just a point in time where space was dense enough that light could not pass through it. So the point where the speed of light through space was zero would have been about 15.8 billion years ago. Now we look at the other end of this graph, we can see that as time goes on, the speed of light is actually going to increase. And so we can use this theory to predict that in about 50 years' time, the speed of light will actually be 1 meter per second faster than it is now. And that's because the density of space, the optical density of space, is decreasing. So the speed of light is actually traveling faster as the universe expands. So that's light. Let's summarize that quickly. So what do we want to know about light? We want to know if it's a wave, a particle, or both. We want to know how the waves can travel or how light can travel through a vacuum, and we want to know why the speed of light is constant. And so using this theory, we can answer all those questions. We can say that light and all electromagnetic waves are simple mechanical waves which aren't traveling through a vacuum, they're traveling through a medium of space. How does light travel through space? It travels through space because space is a medium. It cannot travel through a vacuum, just like all other mechanical waves. Why and how is the speed of light constant? The speed of light is constant because we are motionless in space, and so when we measure the speed of light from Earth, we always measure it at the same constant rate. But the speed of light is not constant, it is variable, and it only appears to be constant because we are motionless in our surrounding space. Okay, so that just leaves us with time. So let's see what we need to know about time and where we can go from there. All right, so why is time variable? Why does time change with velocity? And why does time change with mass? Well, that is all based on Einstein's theory of relativity, which is dependent on the fact that the speed of light is constant. And so because we think the speed of light is constant, we use light as a perfect measure of time. And if the speed of light is not constant, then it is not a perfect measure of time. So as we manipulate light by manipulating the medium of space that it is traveling through, i.e. gravity, or if we manipulate how we move through the medium, or the medium is moving around us, then that will manipulate how our light travels through space, and therefore it will manipulate our clock. And our clock will no longer be accurate, and so we have not changed or manipulated time, we have changed and manipulated the speed of light, and therefore how accurate our clock is. We can think of this as manipulating any clock. So if we used a siren and we looked at the light and the sound of the siren to measure time, then if the siren came towards us, due to the Doppler effect, it would appear like time was speeding up. And if we had the siren moving away from us, then the sound and light would be moving away from us. And due to the Doppler effect, it would look like time was slowing down. If we were using a wind-up clock and we forgot to wind it up, then it would no longer be accurate and it would not be keeping accurate time. If we were using the rotation of the Earth around the sun and this sun, the velocity changed, or we sped up or we slowed down, then we haven't physically changed time. We've only changed the units that we were using to measure the time in the first place. And so when we look at Einstein's light clock and we manipulate the speed of that clock by moving through a medium or by standing in an area of high gravity where the medium is moving relative to us, then we're manipulating how the physical clock works. We're not changing or altering time in any way. We're just changing how we measure time using light. So we can now say that gravity is not the curvature of space-time, but the speed of light is not constant, and therefore general relativity, unfortunately, no longer applies. And so there is no such thing as time dilation or length contraction, and we can go back to the good old days where time is constant and is a universal constant throughout the universe. So time is the same for everyone, everywhere, inside the universe, outside the universe, before the universe was created, after the universe will be gone, and inside a black hole. There is no changing or variability of time. Okay, so I think we have finally covered everything for this lecture or this talk. So in summary, we wanted to create a single interconnected theory which can help us explain and understand the universe. What did we want to do? We wanted to take these observations, take these questions, and put them all into one simple, easy to understand model. So have we done that? Well, we know the universe is big, expanding, and accelerating. We know there's dark matter, and we know the mass is evenly distributed. Now we can understand why, and so we can think of our universe as a single finite mass of space. We can think of space as a state of matter, just like a gas, and we can say that the universe is expanding because it has a pressure gradient between the pressure inside our universe and the pressure outside our universe. So there's a higher pressure gradient of space inside our universe, and therefore it expands outwards. And while that pressure gradient remains, it will continue to accelerate. We know the universe is finite because it is expanding, and we now know what dark energy and dark matter are. So we know why the universe is expanding, which is dark energy. We now know what dark matter is, and that is to do with gravity and how we understand gravity. So what is gravity? Gravity is the movement of space in any given location. And so as the space moves at a set velocity and a set direction, we get the accompanying force of gravity that goes with it. And on places like Earth, our solar system, and in stars, that gravity is consumed. So that space is consumed from every angle and every direction. And we can calculate the force of gravity as the volume of space consumed divided by the surface area which it's traveling through, which in the case of an individual object is a sphere. So surface area of sphere. It's different for galaxies where the mass is distributed differently, and therefore this gravity or the consumption of space is consumed differently. And so we can work out the gravitational rotation, galaxy rotation curves in a galaxy by adjusting the distribution of gravity for galaxies. We can also work out how gravity works on a particle level now that we understand that mass is consuming space, causing the force of gravity, and so we can think of an atom as consuming electrons for energy, creating the force of gravity on a particle level. We also understand waves and electromagnetic waves better now, knowing that they are in fact mechanical waves and that they cannot travel through a vacuum, and that the reason we think they're traveling through a vacuum is because space is in fact a medium of particles. And we now know why electromagnetic waves travel at a constant speed through space when we measure them relative to Earth, and that's because Earth is not moving relative to the space it's surrounded in. We can now understand time much better as we can throw away all the complicated thought experience of Einstein and his relativity we can now say that time is constant. It has nothing to do with motion. It has nothing to do with gravity. It's just that we were measuring time using light, and light is a mechanical wave. So we can throw out general relativity, bring back the Doppler effect, and understand the movement of light that way and how it affects time. And now we can put all these things together. We can take the universe, we can take gravity, mass, dark energy, dark matter, gravity, electromagnetic waves, light, and time, and we can put them all into a single, understandable model of the universe where they all are interconnected, logical, and make sense. So have we done it? Have we created a single interconnected model of the universe? Well, a good model is built on sound principles. So our principle is that space is a medium, the universe is a mass of space, and that gravity is the consumption of space due to mass. Everything is connected through these principles. So yes, we can now explain the formation, movement, and distribution of the universe. We can now explain gravity on a galaxy level, on a particle level. We can explain electromagnetic waves. We can explain why the speed of light is constant. We can explain why time and space appear to be bending due to movement and gravity. And we've interconnected it all into a simple logical explanation. Do we have exceptions to the rules? I don't think so. I haven't gone into a lot of topics. I haven't done anything to do with quantum mechanics or particles, really. I've covered a lot of that in my book. I wanted to keep this as short as possible, and I already know it's way too long. And once we have a topic, we should understand how it works, and it should be logical and simple. So I know that's probably not the case for you hearing this the first time, very quickly and briefly. And so I think once we start thinking about these concepts, this will become more obvious to people as this video is distributed to more and more people. Okay, so that's it. If you're still here, thank you very much for watching. I really appreciate it. I hope you took away a lot from this presentation. I know it was very quick. I know there was a lot to cover. I know I didn't go into everything in a lot of detail. What I have done is I have written a book which goes into much more detail, uses more data, has all the maths. It's simple, it's easy to read, but I cover a lot more topics in a lot more depth. And so if you are interested in anything that I've said today, or one, I'm absolutely thrilled. Thank you. Two, I've attached a free link in the video to a PDF of the book below, or you can buy it on Amazon and help support me. I've had a lot of trouble getting this out and getting anyone to pay attention or listen to me, and so every little bit helps. Unfortunately, I'm not a physicist. I'm not affiliated with any universities. I have not been able to get any work published because, again, I'm not affiliated through any universities. I haven't been able to talk to any physicists because they're just not interested in talking to someone, again, who's not a physicist and doesn't have experience in the matter. And so if you found what I said interesting or helpful or useful in any way, it would be really appreciated if you could pass this video on to as many people as possible, because I want the word to get out, and I am trying my best to talk to the appropriate people, and unfortunately I don't have a lot of those avenues to go down. So the more you can share this video, the more you can tell other people about it, the more I can get people interested. Hopefully friends or family or someone has some connection to university students or physicists or physics departments, and if we can get this distributed to them, then hopefully one day someone will take these ideas seriously, and we can help understand the universe in a simpler, more complete and interconnected way. So again, if you can share this video, like it, or have a look at my book in the link below, I would very much appreciate it. Thanks again for listening. Appreciate it. Have a good one.